Hello, ladies and gentlemen. Welcome to our meeting. This is fifth lecture on electroacoustics, and today we are going to talk on sound propagation in the air, as well as room acoustics. Next week we'll be talking about noise control, especially in the rooms. And if we have some time, we can make some repetition of the important things for the test, which you are going to write on the 13th of April this year. And it will be the test number one. I think that everyone of you will pass this test, and so of course I hope that you can be prepared for this test. Okay, so let me show you the presentation. I think everything will be all right. I hope it works, but if something is wrong, please tell me know. Okay, I think it's good.
It works, yes.
Oh yeah, thank you. The first time in this semester, but you know, I had to reinstall my Zoom program, so it was something wrong with my Zoom platform. Okay, so sound propagation in the air. Of course, when we make some assumptions for lossless sound propagation, as follows: that there is no inner friction, which means there is no viscosity in the medium. It is the first assumption. The second one is that is negligible thermal condition, and the medium is works as a perfect gas. So we can talk about the lossless sound propagation. Of course, it goes without saying that these assumptions are not strictly valid in real fluids, in real media, of course. So therefore, we have to consider the following three reasons for dissipation. First of all is viscosity. Second one is thermal condition, and deviation from the perfect gas. Of course, in the air, we can talk only about longitudinal waves, and only for this kind of waves our consideration would be applied. So the plane wave solution can be expressed as a pressure of sound, and this pressure in a particular place and at a particular moment of time, it could be expressed as a maximum pressure, and e to the power of absorption coefficient multiplied by the actual measuring point position. And so there's a complex operator, which means that sound pressure is such kind of a complex value. And so due to not ideal situation in a real medium, we can talk about the real viscosity. So this viscosity of a fluid is a measure of its resistance to gradual deformation by shear stress. Of course, some heat or thermal conduction also exist. And it is a transfer of thermal energy from the compressed and thus warmer zones to the expanded and thus cooler ones. In consequence, the compression is no longer strictly adiabatic, and hence pressure differences are attenuated. So this simply leads to dissipation. And the damping coefficient of the air into meteorological conditions expressed in Nippers per meter, Nipper as a unit is expressed, is shown in this table. Please notice that the differences between lower frequencies and higher ones from the region of audible frequency, these differences are greater, and for 16 kilohertz, we can talk that that the damping coefficient is higher, about 100 times than in the case of the lower frequency. So higher times Nipper, of course. And some to show you in a real relations between what's happened to the lower or higher frequency, let me show you some example of attenuation. If we are 100 meters from some event with a broadband sound source, and we are at 20 degrees of Celsius, so the attenuation of the sound could be at 1 kilohertz of a half of decibel, and about for 1 kilohertz, and for 16 kilohertz, this attenuation is 33 decibels. So it means that in relations to the 1 kilohertz, for 16 kilohertz, the damping is about 15 or 20 times greater than for 1 kilohertz. So you can notice that if you are, for example, in such open air event as some open concert, so in the larger distance from the stage, you can perceive mostly the lower sounds as a bass, as a bass drums, etc. But the higher sounds are mostly damped, and of course you can hardly perceive this range of frequency. And of course at 10 Celsius, the difference between this attenuation is greater. So Please remember that for higher frequency, the damping is more effective than for a lower frequency. And when we have such case of propagation of the sound, we can talk about reflection and refraction of the sound wave. In this situation, as shown in this picture, we can notice that the incident wave here goes to the barrier between two media with different impedances, and the reflection occurs, and the reflected wave goes from this boundary with a equal angle to the normal to the boundary of between two media as a incident wave. So the rest of the incident wave can be go into the second media, and of course we can discuss on some diffraction and some damping, etc. And the situation we are interested in is only when between two media with various or with greater differences in acoustic impedance. So this incidental wave reflects from this boundary and goes outside of this barrier, and of course not only the flat barrier could exist, but we can meet also a moderately curved plate, and we also can talk that incidental angle of the wave is equal to the reflected angle of the wave. Of course, the condition is that curvature should be greater than length of the wave. And we very often in acoustics use some phantom source for modeling the character of reflecting sound. As you can see in this picture, if we have some source, real source, and we have here the receiver, in this case the microphone. So we can distinguish two waves of sound propagation. First of all, this is the direct sound, so it means that directly from the source to the receiver, and the second one goes as an incidental wave, and it is reflected by the reflecting plane and goes to the receiver with some time delay, of course. And as you might have noticed, the angle of incidental wave is exactly equal to the reflected one. But we can model this phenomenon without using some angles, but with use some mirror or phantom source. And the phantom source is the source, which is symmetrical in the reference of the reflecting plane, and it is opposite in this position. And of course, the direct sound is going directly to the receiver, and the reflected one is modeled in this part as a reflected wave, but in this part as a distance between the phantom source and the point of reflection. And of course, it's more easier because of the fact that we don't have use some angle in the modeling or in the drawing with these rays of sound wave. So this is reference line as a reflecting plane, and every active source can be mirrored due to this reflecting plane, and should be could be represented by phantom sources here. And of course, the results will be the same. As I said, it's more easier to draw this situation. And when we have some sound reflections, we can talk about three cases. I mean that focusing, scattering, and scattering with a convex surface. In the case of concave, we can the similar situation of the concave mirror in the optical. I mean, when we have the sound source in the distance between the radius of the mirror and the half of this radius, we can have some focusing of the rays. In this case, the rays of the sound wave. And when we have the sound source in a smaller distance than half of the radius, we can talk about the scattering. So the sound waves is completely reflected and scattered by this concave. And the same situation occurs for convex surface, as is presented here. But in this case, we don't so when this sound source is in a distance of the radius of the half of radius, etc. So we can discuss only on the scattering sound wave, and this scattering occurs by the reflection of the convex surface here. And some rules which are very important from this point of view are that focusing of or scattering may happen as a result of curved surfaces. And of course, the very important for us is that unwanted echoes caused by focusing can be avoided by modifying the form of the surface and employing irregular reflecting structure or by covering the surface with sound absorbing materials. Let me tell you a few words about the echo. The echo appears when we can distinguish by our human hearing system two sounds. Going directly from the source, and the second one is reflected. So when the time difference between these two acoustical events is greater than 10 milliseconds, we can say that some echo sound would be perceived by our hearing mechanism. So to avoid this echo, we can use some absorbing material here in this side of the surface. And of course, this situation can be applied for convex surface as well as concaves in the case of scattering. But this absorbing material can reduce the amplitude of the echo signal. And this reduction may be very effective, and we cannot perceive the echo signal as a separate one. Well, if we listen to the music, so the echo is not some disturbing effect, but when we listen to the voice, for example, when we listen to speakers, so we can make some confusion between the intelligibility of spoken words because of the two signals which are mixed, and this echo should be removed or should be limited in amplitude to separate from the original signal. So I can show you some algorithms for echo eliminations, but I'm going to present you at the end of my part in the second part of semester. And such effects of sound reflection, you have to remember these effects. So focusing or scattering may happen as a result of curved surface, not in a plane surface. And about unwanted echoes caused by focusing or scattering the sound wave. And how about the sound absorbing materials? These materials are generally some kind of porous materials, and you have the four examples of sound absorbing materials widely used in acoustics adaptation. For example, fully reticulated plastic foam, partially reticulated plastic and wool. And you can see the structure, the mix in general. And so this structure of the material, the features in that way that they can absorb some sounds. And the coefficient of absorption of porous materials uh, are presented here in this picture, in this graph, and you can here the number of the curve reflects the dimension of this porous material here. And we have the incident wave, and of course the reflected sound, and we have here the porous material on some solid structure. And you can see that the absorption coefficient goes higher for lower frequencies if the thickness of this porous material is higher. So the general rule is as the thickness of the porous material increases, the coefficient shifts to low frequencies, and the sound absorption for low frequency is more effective. Of course, for higher frequencies, we have a good and some we have the most and almost equal effectiveness of the sound absorption. To increase the absorption of the sound, we can use also some structures, some devices, and some equipment for improve this absorption. And on the left you can see the Helmholtz absorber, and this is a typical Helmholtz resonator. As you remember from the first of the second lecture, we have some masses, acoustical masses, we have the acoustical resistance, and we have some chamber here with acoustic compliance. And such unit on the wall, for example, increases the absorption of the sound, as well as some membrane absorber presented here on the right. And we have some membrane with some solid material, and between the wall and this membrane from the solid material, we have for example, some absorbing material, as in most cases mineral wool, and we have here acoustical compliance, and so we have also discussed on the some kind of Helmholtz resonator, but without some acoustical mass. In this case, we have three elements: mass, resistance, as well as acoustical compliance. And here we have only acoustical resistance and acoustical compliance without acoustical mass, but due to reflection of the sound on the surface of this membrane, the total energy of diffraction of refraction acoustical wave is smaller than in the case of this part. So if we want to have some electroacoustical analogies and some electric circuit, we can here have the series connection of acoustical mass, resistance, and the capacitance. And in this place, we have only acoustical resistance and the compliance here. So we have here the series connection as a RLC electrical circuit, and in this case, for membrane absorber, we have only a kind of low pass filter with a resistance and capacitance. And the characteristics are as follows. If we don't have any absorbing material here in this chamber, we have very narrow the resonance curve, and so the damping or the absorption is very effective only for narrow band of frequency. In this case, about 100 hertz. And when we use some absorbing material here in this chamber, this curve becomes more blurred, and so we have here the effectiveness of the absorption in the wider frequency band. In this case, from lower frequencies to the 500 frequency. And of course, if we fill this chamber with some absorbing material, so such device makes this absorption more effective. And once again, types of reflection of acoustic waves from the walls, if we are talking about the real room. When we have some absorbing material on the wall, we can talk about the incidental wave, so the direct sound, as well as a part of reflected one. And this reflection is attenuated. And of course, the directivity of this reflection signal is strictly depends on the angle of the reflection. The similar situation occurs when the sound is reflected in greater part than in a case of absorption, and so we can see this fact in this picture, in this characteristic, when we have some direct sound and some specular reflection. Please compare the amplitudes between this situation and this one. So there is a difference of mostly 12 decibels between the amplitudes of absorbed reflections and the reflection of this situation here. And directivity is thus more wider than in the case of totally absorbed signal. And when we have a totally diffused sound, we have direct signal and a lot of diffusion, and we can distinguish some dominated dominated direction in the directivity characteristic in this case. So we can talk about absorption when the small portion of the sound comes from the wall, and reflection of the sound in a real situation, as well as a diffusion situation here when the sound is reflected and it goes everywhere. So if you visit during the laboratory our anechoic chamber on the 6th floor in the C5 building, you can see the walls constructed as some structure of absorbers, and you can feel that the lack of reflected sound makes you some strange feeling, you know, if you are in such places, and if you are talk to each other, you can listen to mostly the the direct sound, but some reflections are damped, and you don't feel comfortable in this situation. I hope that Michał is going to Michał Uczyński is going to take you on the trip to our anechoic chamber in our department. And so, how about the guiding of the sound in the real room? As you can see in this picture, we can talk about the reflection of the sound, and of course we have here some source in the speaker in this case, and this sound in the whole auditorium is guided to the audience directly, and of course via ceiling. And the ceiling is reflected in this case. So two examples rays are depicted for the illustration. We have here two phantom sources created on the base of the typical placement of the speaker of the source, and you can imagine what's the rule of this phantom source is here in this picture. So we can draw this sound ray with the use of the angle, but we have to measure this angle, but without this it's easier for us to make some phantom source, and on the base of this source we can construct the sound array here with the use of this phantom. And it was only example of the real auditory room, or in a real place, and on the theoretical consideration, we very often use some cuboidal resonator, and of course some resonant frequencies could be written as in this formula, and these resonances influence the sound level which is going via our room, and reverberation time for particular frequency is greater if this frequency is a resonant one. I mean that when some sound is equal or is near to the resonant frequency, it's as this room behaves as like as a resonant circuit. For example, if we have some signal equal to the resonance frequency, you know, this electrical circuit goes to resonate, and the same situation is for room acoustics. And when we have the frequency of the acting signal, which is different than a resonant one, so we can make some coloration of the sound due to for example, different behavior from the acoustical response of the room in comparison to the direct signal. So we can talk about the changes in sound colors in of the source. And how about the rise and decay of sound in a room? When we switch on the sound source, so the sound is not acting immediately. So it needs some time for the situation in the real room, and this rising time is necessary to achieve the steady state of the sound level. And when we switch off the source, we can talk about the reverberation of the signal, or release the signal, or decay of the signal, and so this signal disappears, and the shape of disappearing is important from the sound quality in a real room. And in the real situation, we have such example of switching of the signal, and we have some fluctuation of the sound, and after the switching off, we have disappearing of the sound, and the sound has its amplitude, which goes to zero, and we can express this as a decreasing sound level. And as a theory says, we can talk about the reverberation time, and this is a very important unit for quality of the auditory or the concert hall, or some room from the acoustical point of view. And we can measure, of course, this reverberation time when we have some steady state of sound level, and when we switch off the source, so the sound can disappear. And when the sound level reach the level minus 60 decibels, so we can talk that the time from the steady state to the minus 60 decibel means that it is a time reverberation. Of course, in a real situation, it's very difficult. It's very often the difficulties occur, and for example, as a acoustical noise, etc., etc. So we can talk about, for example, reverberation time, not RT60 or RT30. So it means that we measure the decay of the sound level to the value of the 30 decibels, and we approximate as a straight line and hypothetic value, which is equal to minus 60 decibels to determine that RT 60 reverberation time. But in the theory, you can consider this situation that everything is possible to measure, and some unwanted sounds don't appear and don't disturb our situation of the measurement. And so some formulas for this reverberation time are presented here in this picture. And so independence of on the real condition and the volume of the particular room, more or less this formula can describe the real situation in more or less accuracy. And so the very often used formula is a formula made by Sabin, and we have here presented in this place, and by Eyring. These two formulas are mostly used in room acoustic designing. Knudsen took into consideration the absorption in the air, and the formula by Knudsen could be applied for large areas and for large rooms. And in the typical situation, if you design some places, for example, on the engineer study or engineering practice, you can use with a good accuracy formula by Sabin or by Eyring. Independence on the absorptivity of the acoustic, because you know it's mostly the same values with a difference between coefficient of absorption. Formula by Sabin is applied mostly for smaller absorption coefficient, while the Eyring formula is for more damped rooms with higher values of absorption coefficient. Of course, this coefficient varies from practically from 0.1 to 0.9. And if we have some alpha less than 0.2, we can simply use the formula by subbing here. And room resonances could be presented also as a plot of some computer simulations. And you can see that we can distinguish some modes of resonances in a typical real room. These pictures are taken from some diploma thesis of one of my colleagues, engineer, few years ago. He or she made some modeling of the real room. And so when the sound fills the room in a steady state, it may be also presented as some kind of echogram. So it could be presented as a set of acoustical event, and we can distinguish the direct sound, some early reflections, and some late reflections or reverberation toil, as it's known in the trade. So to be more accurate, we can distinguish the direct sound. It is the source, and for example, in this place we can set the point of observation or some receiver, and the direct sound is the sound which comes directly from the source to the receiver. And in this case, we can distinguish the eerie reflections as reflections from ceiling, in this case 2 of them, and lateral reflections from the walls, and we have here 4 reflections, and of course the reverberation tile as a set of some undistinguished echo signals which produce some kind of continuous sound characteristic for disappearing of the sound. And here on the y-axis you can see the levels, but there are only examples of the values of direct sound as well as eerie reflections and reverberation. And of course, as I said, the reverberation time makes the particular room weaker or better for perception of different kind of presentation. In this diagram, you can see that for organ music and some choir music, in respect to the volume of this hall, that reverberation time is preferred, has the greatest values than, for example, for speech, due to, as I said, intelligibility of the speech, and for cinema, preferred reverberation times are graded. For theater, because they involve the speech signal mainly, the preferred reverberation time are greatest, and multiple pores as a auditory greatest too. And for orchestra music is between the organ music and between the speech. So we can say that orchestra auditorium should feel some acoustical condition between the church, because you know the organ music is played mostly in the churches, and the dry auditory, typical auditory halls for speech. So some compromise should be achieved for the orchestra music presentation. And how we can design the room acoustics. And the examples of the reflected area here in the shaping of the ceiling is presented here in this picture. We have a source, and of course we have to take into account the reflections of the ceiling. And as you can see, we can have here from this part of ceiling, this part, and of course some ground floor, as well as the first balcony and the second one. And there is equal sound equally covered places here. I mean, due to the balance between the direct sound as well as reflected sound. Of course, from the ceiling in this place, in this case, but when we do to make some cross section not this kind of cross section, but perpendicular to this one. So we can consider also the reflections of the sound, and we have to consider. We have to take into consideration the reflections as a good sound coverage of the whole auditory area. And if we have some large halls, we can say on also some reflecting area here. Because this reflector works as a natural sound amplifier. Well, ancient Greek theater features in that way that except for the large hall of large area of the open air and the stage from which the actors are speaking to the audience. This backstage normally has some kind of acoustical reflectors, and the example of this reflector is presented here in this picture as this solution. In a small hall, it's not necessary to have some acoustical reflectors, as is presented in this picture. And so, for large halls, this reflector is very often needed. And the example of wrong acoustical condition is presented here in this picture, and we have such phenomena as a acoustical echo, which returns to the source, so in this case to the speaker, and this is reflected by this this part of the ceiling and the back wall, and goes back to the speaker, and long delayed reflection here in this signed as a number 2. Acoustical shadow, the area named on the 3 number. We don't have here any reverberation and any reflected sound, and only the sound coming directly from the stage can go to this area, or some sound concentration due to acoustical, like a mirror here in the ceiling, which causes the concentration of the sound and unnatural amplification in this row in the second floor of the audience. Of course, it's only examples of wrong designing of large halls, and so you can notice that this area is not recommended for design. And at the end, I want to talk something about the critical radius as a very important element for acoustical design. As you can see on, for example, on this picture or in this one, we can distinguish the direct sound as well as a reflected one. Goes in this case from the shaping ceiling, and the direct sound has some energy, as well as the reflected sound also has some energy. And the place in which these two kinds of energies are in equilibrium, so we can call the critical radius. And of course, it's very important for the places with large reverberation time. For example, in the church. If you are going to the church and if you want to talk, to record somebody talking in the church, you can place your microphone near the sound source. Why? Because when the reverberation time is greater, is higher, so we can have a lot of reflections from the walls, from the ceiling, etc. And so the energy of reflected sound is greater than from direct sound. And you have to remember that the reflected sound contains of a lot of echoes and some reverberation, and you may some problems in intelligibility of the spoken words. So in the case of the meaning of some recording, some speaking voice, we must place our receiver or our microphone in the distance that is near, that is smaller than the critical radius here. When we have the energy of the direct sound greater than the diffused field energy. So it's some practical instruction for you that if you, for example, have some wedding ceremony and you have to record this. So please place the mic, your microphone. In the near field of the source and not far away from the source because you you may not recognize properly every spoken words produced by speaker. Due to increase of diffuse energy of the diffused sound. And at the end is a flutter echoes as a very unwanted sound phenomenon. And the flutter echo occurs when two walls are parallel. And the specific kind of echo can be produced. You know, we have the sound source, and so the sound is going to the this wall and as a reflection to this one, etc. as a ping pong. And so it every reflection produces an echo signal, and as a series of this individual echo should be distinguished by our human hearing organ, and we can perceive this series as a fluttering echo. You can meet this phenomenon, for example, in the bathroom or in the shower, and you know what I mean. It is unpleasant sound, and of course, this sound is unwanted in special situations, as in studio rooms, and in such cases as concert halls. So the origin is two walls which are parallel each other, and the sound source is between these two walls. And this is a simple way to produce the flutter echo, which is some unwanted aspect of the acoustical sound. And to avoid this phenomenon, we can slightly move these two opposite walls on the angle more than 5 degrees, or by making surfaces absorbing or scattering. So, as I said, that you know, in the bathrooms we have some ceramic on the walls, but it will be very strange to make some absorbers on the bathroom walls made by, for example, mineral wool, because of humidity, etc. So, most important things to remember from our today's meeting. So we can remember some main aspects of attenuation of sound in the air. So and especially the phenomenon which occurs for higher range of frequency, of audible frequency, in respect to the lower one. So the higher frequencies are attenuated more than lower frequencies. And definition of time reverberation, what's that? And what's that, the critical radius distance? And you also have to know the phenomenon of flutter echo as an unwanted sound. Okay, that's all from me for today. And if you have some questions, so please, please give me this or not. You can also write to me via email, so I can also answer. So next time, next week, we'll be talking about noise control in respect of some acoustical adaptations of the room, and if we have time, we can make some repetition from the all the aspects of the material, which is going to be under the test in 2 weeks. So if you don't have any questions, so goodbye.
Thank you. Goodbye.
Thank you. Goodbye.
Goodbye.